Yeah, so deadlock occurs when there is a set of processes which are waiting for each other. So there is like each process is waiting for some other in the group, some other process. And naturally, none of the processes can proceed because everyone is waiting for someone else. And we saw some examples like this. So suppose there are two processes, one of which asks for the tape first and the other asks for the printer. And suppose the tape is allocated to P0 and the printer is allocated to P1. So then now P0 requests for the printer. So that means P0 is waiting for P1 because the printer is already allocated to P1. Conversely, P1 has now requested for the tape. So that means P1 is now waiting for P0 because the tape is allocated to P0. So here P0 continues to wait for P1 indefinitely, and P1 also continues to wait for P0 indefinitely. So this is an example of a deadlock. And of course, this can happen also with semaphores, mutex locks, and so on. This is what we have discussed. So now let us formally understand what deadlocks are. So these were just examples. So how to characterize a deadlock situation. So for a deadlock to occur, 4 conditions should hold simultaneously. Okay, so these are necessary conditions. Again, these are not sufficient, as we might see soon, but these are necessary conditions. So these 4 are the conditions. One is mutual exclusion. That means only one process at a time can use a resource. So if every resource in a system is shareable, then there is no possibility of deadlock because every, say, resources like read-only files, they never cause deadlocks because many processes can share them. However, like writable files, mutex locks, devices, these are things which are not shareable simultaneously. So there should be, for a deadlock to happen, there should be some resources which are exclusively required by the processes. Second condition is hold and wait. That means this is what the processors do. They hold a resource and then they wait for another. So just like in the previous example that we saw, one process was holding the tape and then requesting for the printer, right? So hold and wait. Third condition is no preemption. So the word preemption is familiar to us. We have discussed this multiple times. So here we assume that the system is not such that the OS can preempt some resource from a process. So for example, let's say, we will discuss this, but suppose a process is holding the tape and requests for the printer. Now, suppose the OS understands that a deadlock is about to occur, suppose in some way, and it preempts, it does not give the tape to the process. Also, it preempts the printer from it, the OS. So in this example, going back, let's say here, suppose P0 has asked for the tape and has been allocated to it, and printer has been allocated to P1. Now, P1 requests for the tape. Suppose in some way the OS understands that a deadlock might happen now. So the OS does not allocate the tape to P1, and in fact, it preempts the printer from P1. So the OS takes back the printer from P1. Right? So if this can happen, then there will be no deadlock. At least deadlock can be prevented. Right? So for a necessary condition for a deadlock to happen is that this kind of preemption is not allowed. Okay. So you might understand intuitively that we are not only discussing deadlocks, we will also discuss ways to prevent deadlocks. So I guess you are getting some idea of what can prevent a deadlock also. Say, suppose if resources are preemptible, or if the OS is designed in such a way that it can estimate that deadlock is likely to occur and therefore start preempting resources, that might be one possible way of preventing deadlocks. So those things will come later. But so these are the necessary conditions for deadlock. Remember, we are not discussing yet how to handle deadlocks. We are discussing the necessary conditions. So no preemption is a necessary condition for deadlocks. If preemption is allowed, then deadlocks might be prevented. The last condition is circular wait. This is what we were discussing. So there is a set of processes such that every process in that set is waiting for some other process in the same set. So there is a cycle, like P0 waiting for P1, P1 waiting for P2, P2 waiting for P3, and so on. Ultimately, Pn waiting for P0. Right? So there is a cyclic kind of dependency or a circular wait. So in that set, every process is waiting for some other process in the same set. So these are the 4 necessary conditions for deadlock. So remember these, because when we will talk about ways to prevent deadlocks, then one way is to ensure that at least one of these conditions don't hold. Right? So we will come to that, but for now, let's remember that these are the 4 necessary conditions for deadlock. Now, so fine. So these are the 4 necessary conditions for deadlock, but how will you computationally understand that there is a deadlock? Just by noting down these 4 conditions won't help you to compute or won't help the OS to computationally understand that a deadlock has occurred. So how can that be done? There are multiple ways, one of which is a graph-based method. That is what we will discuss. For this, we create a specific graph called resource allocation and resource request and allocation graph. So for simplicity, this is called the resource allocation graph. Okay. So how does this graph look like? So in general, when a graph is to be defined, people define the nodes and the edges, the vertices and the edges. So what are the vertices in this graph? The 2 types of vertices. One is the process nodes, right? So the processes that are active processes in the system, they are nodes and they are denoted as circles. Another type of nodes are the resources or the resource types. They are denoted as squares or rectangles. Okay, so processes and resource types, these are the nodes. And what do you think are the edges intuitively?
Process requesting first.
Exactly, and anything else? So process requests for an edge, process request for a resource, an edge is added. Anything else comes to your mind? When a process will release a resource, the edge can simply be removed. But there is another step in between. The OS allocates the resource to the process. Okay. So exactly these are the 2 types of edges. Request edge, that is an edge directed from a process to the resource. So PI arrow RJ means the process PI has requested for one instance of resource type RJ. Okay, and is waiting for it. And the assignment or allocation edge is the opposite. So a directed edge from the resource to the process. Okay. Quick question here. See, this could have been 2 completely different types of edges, like edge type 1, edge type 2. Instead, it's just like what is being done here is just reversing the direction in some way. Right? Any idea why? Why is the direction being reversed instead of bringing in a new type of edge?
Lesser computation because
lesser computation. Yeah, well, okay, but I mean, maybe that's not the key motivation. You are right in a graph sense, yes. Anything else? Exactly. Good answer. We'll come to it. So, okay. So understand that the request when so when a process requests for a resource, an edge is added from the process to the resource, and when the resource is allocated, the direction of this edge is changed. Okay. Why? This is what Shivashik answered, but we'll come to it. Okay. So this will how the graph will look like. A process would be a circle. A resource type would be a rectangle, and the number of instances of the resource that are available, we will show them as squares in the rectangle. So this is just to say that, okay, there are 4 instances of this resource type, the second picture here. And then when PI requests for an instance of RJ, there is an edge added. And when actually one instance of the resource is allocated to PI, then the direction of the edge is changed. So now using this kind of a graph, how to actually understand if there is a deadlock. So this is an example of a resource allocation graph. Okay. Do you now get some idea on how to understand whether there is a deadlock in here? So this question is related to the previous question I asked, that why were we reversing the direction of the edge?
like if I requested a resource and it was allocated to me, the requested is deleted.
You might say that, or you might say that the direction of the edge is changed.
Okay.
That is why I was asking. So it could have been that you delete that edge and you bring in a completely new edge. Instead, we are reversing the direction of that edge. That is why what I was asking, why. So this slide should give you the answer to that also. Essentially, we are looking for cycles in this graph. Okay. If there is a cycle in this kind of a graph, it might indicate a deadlock. I'm not saying it will, but it might. Right? So if you see here, what is going on? So P1 is waiting for R1. R1 is allocated to P2. Now P2 is waiting for R3. R3 is allocated to P3. And P3 is waiting for one instance of R2, whereas R2 is, the two instances of R2 are allocated to P1 and P2. Okay. So essentially every process is waiting for some other process in this set. And the way to understand this computationally is by looking for a cycle in this resource allocation graph. Right, so this is why the direction of the edge was reversed, so that we get a cycle. Okay. Right, so a cycle in a resource allocation graph may indicate a deadlock, but it is not a sufficient condition. That means there may be a cycle in the graph, but there is no deadlock. Here is an example. See and tell me why is, so first of all, see that there is a cycle here between P1 and P3. I mean, P1, R1, P3, R2 is a cycle. But there is no deadlock here, I claim. Why? Do you agree that there is no deadlock here?
Because the CPU is able to allocate.
A bit louder.
Like in R2, there are two instances, so the CPU is able to allocate to them individually.
Exactly. So suppose P2 or P4 finishes, they complete. So they will release either an instance of R1 or an instance of R2. And that can be used to satisfy the other requests. Right? So even though temporarily there is a cycle here, other resources, some instances of the resources can be freed once P2 and P4 completes. Right? So a cycle is not a definitive proof of a deadlock, but if there is a cycle, there may be a deadlock. Okay. So this is a computational way of figuring out if there is a deadlock in the system. So this is the what we understand. If the graph contains no cycles, then completely sure that there is no deadlock. If the graph contains a cycle, then there are two cases. If there is only one instance per resource type, then there is a deadlock. Right? But if there are multiple instances per resource type, then there is a possibility of a deadlock, but not sure. This is the case which we saw in the previous slide. So if every resource type has just one instance, then having a cycle denotes a deadlock. But in the previous case that we saw here, resource set had multiple instances, and therefore there was no deadlock even though there is a cycle. Right? Okay, so this is how to detect deadlocks. So you have understood what does deadlock mean more formally and how to detect it computationally. Now we will come to the more important question of how to handle deadlocks. So there are two broad mechanisms of handling deadlocks. One is prevent deadlocks. The other is if a deadlock occurs, then handle it. Now the first type of method, which tries to ensure that there is no deadlock at all, and a deadlock will never occur, that has also two flavors of approaches. One is called deadlock prevention, another is called deadlock avoidance. So deadlock prevention is, you remember those four necessary conditions that we discussed for having a deadlock, ensuring that at least one of those conditions will not hold. That is deadlock prevention. And deadlock avoidance is the kernel analyzes the current resource allocation state, like which processes are there, which resources are allocated to which process, and so on. And then it determines whether granting a resource request might lead to a deadlock later on. So here in the deadlock avoidance, we will see the details, but in deadlock avoidance, the OS can refuse a particular resource request from a process. saying that, okay, though the process is, maybe the process has requested for a resource which is free, but still the OS can tell I'm not going to allocate it right now because this might lead to a deadlock. Right? So essentially in the second deadlock avoidance style of methods, the OS controls when resources will be allocated to which process. Even though they are resources might be free, they might not be allocated. So these two methods are like a prevention is better than cure kind of thing. So prevent deadlocks. And the second type of method is cure. That means detect that there is a deadlock and then take steps to resolve it. Okay, so we will see some more details of these methods now. So let us start with the simplest deadlock prevention. So the key idea is prevent one of those 4 necessary conditions from existing. So basically we are looking to falsify one of those conditions, one of those necessary conditions. How to falsify mutual exclusion? Well, this is not always possible. So like some type of resources by nature are shareable, like say read-only files, but some other types of processes by nature are not shareable. Say like read-write files, or say there is only one printer, so something like that. So falsifying mutual exclusion cannot happen always. Falsifying hold and wait can be done in 2 ways. Remember, hold and wait is that a process is holding some resource and is waiting for some other resources. So this can be falsified in 2 methods. A process which is blocking on a request should not be permitted to hold any resource. Okay. So just think about it. We have discussed that maybe a process is waiting for something. That means it is now in the waiting state. Let's say the OS is designed such that if a process is in the waiting state, no resource is, that is not allowed to hold any resource. Right, because that wait can be quite long. So suppose if a process is not currently in a ready state, if it is waiting for some event, then the OS does not allow it to hold a resource and then wait. Right? So if the OS is designed in that way, then it's one way of falsifying hold and wait. The other approach is a bit less practical. A process holding a resource should not be permitted to make additional resource requests. How is that? How is that even possible? Because it might be that a process holding a resource needs something else. So for this kind of a method, it requires that a process to request all resources that it is going to need before it starts execution. So right before, even before starting to execute, every process has to declare what resources it needs, and that those resources will be allocated to it throughout its execution. Then, of course, deadlock will be prevented, but this leads to low resource utilization, as you understand, because maybe the output part would be only needed after a very long computation, but according to this method, the process has to be allocated the output device throughout its execution. So it leads to less resource utilization and usually not used. Right, so of course, resources are allocated only for the minimum time required. But the first method is kind of practical, that if a process is waiting, then do not allow it to hold any resource. Okay, so these are falsifying mutual exclusion and falsifying hold and wait. The other thing is falsifying no preemption. Right, so this is kind of continuation of the previous point. So suppose a process is holding some resource and requests for some other resource. The OS understands that it cannot be allocated right now. So then the OS has the power to take back or to preempt all the resources which were earlier allocated to this process. Because anyway, this process will have to wait. The new resource it is requesting for cannot be allocated right now. So it will have to wait. Therefore, the OS does not allow it to hold the earlier resources. Okay, so those resources are preempted from this process. Even though they were allocated earlier, they are preempted from that process as long as it is waiting. Okay, so this is falsifying the no preemption thing. And finally, falsifying the circular wait condition. So basically the hold and wait cycle. So remember, a cycle must exist, like say P1, P0 waiting for P1, P1 waiting for P2, P2 waiting for P3, and P3 waiting for P0. So this kind of a cycle should exist if there has to be a deadlock. So break this cycle. There are many ways. One way is to impose a total ordering of all resource types and require that each process requests resources in an increasing order of enumeration. Think about it. If this rule applies to all processes, then this circular wait won't happen, because every process is requesting for resources in a particular order. So P0 might wait for P1, P1 might wait for P2, and so on. But that closing loop, like Pn waiting for P0, won't happen if there is an enumeration of the resources, that a particular order, every process has to ask for resources in a particular order, if that is true. Okay, so these were the deadlock prevention approaches, which essentially is to falsifying one of the necessary conditions for deadlock. Yes.
I mean, these all seem like very strict measures. All of them disempower the user from doing a lot of things. So, like,
Agreed.
are they implemented practically?
Very good question. I'll answer it. Okay, that's a very good question. Okay, so this was deadlock prevention, which is falsifying one of the necessary conditions. So now let's go to deadlock avoidance. Deadlock avoidance means that somehow the system has an idea of what is the current state. Is it safe, or is it likely to lead to a deadlock? Or more importantly, maybe the current state is safe. A new resource request has come from a process. Let's say that resource is free, that is available. But should I allocate it immediately? Can that lead to a deadlock later? So this is what the OS tries to judge. So a process requests for a resource. If it is not free, then it has to wait, of course. But just because that resource is free now, should it be allocated immediately? Or might that lead later to a deadlock? This is what the OS tries to reason. Okay. So let's understand how. So essentially, before allocating a resource, check whether this allocation may lead to a potential deadlock in future. Okay. So essentially, what is defined, we will define it as a resource allocation state. So like what are the resources allocated currently to which process, and which process requires more resources? This will all come in under the purview of a resource allocation state. So essentially, the idea is to differentiate between what is a safe state and what is an unsafe state. We will define these. So the OS always tries that the system remains in a safe state. It prevents the system from going to an unsafe state. So what is a safe state, etc.? This is the formal definition. So a state is safe if the system can allocate resources to each process in some order and still avoid a deadlock. In some order, that means we do not always need P0 should finish before P1, but in some order, the processes should be able to complete. Okay. So more formally, suppose there is a sequence of processes like P1, P2 up to Pn, such that for each Pi, the resources that Pi can still request in future can be satisfied by currently available resources plus resources held by all Pj with j less than I. Essentially, what is happening is this. At the current point of time, every process, let's say, is allocated some resources, and they can ask for more resources. So that the OS knows. So for this kind of system, again, the OS needs an estimate of what are the resources that a process will need throughout its lifetime. Okay, the OS needs that information a priority, that for every process, what is the total amount of resources that the process will need. Now, at this current point of time, some of the resources are allocated already to the processes, but they can ask for more. Maybe some processes have been allocated all their resources, but there are some processes which can still ask for more resources. That the OS has to know. So now the OS tries to figure out, does there exist a safe sequence? A safe sequence of processes is this kind of a process. this kind of a sequence where a particular sequence, let's say P1, P2, Pn, or in some order, such that for each Pi in this sequence, the resources that Pi can still ask for in future can be satisfied by either currently available resources or by all the resources held by the Pj with j less than I. So if there exists such a safe sequence, what does that mean? That means, say that resources that Pi can still ask for, they are not available now. But there is no worry, because there is some process with j less than I, there is some process Pj with j less than I, which has all resources already allocated. So that will complete. When that Pj completes, it will free up its resources. That will help the next process in this safe sequence to complete, and so on. Right? So there is some sequence such that, so suppose the resources that Pi can still ask for, they are not yet available. They are not available right now. But there is a guarantee that when all the Pj, j less than I, when they complete, then all the resources required by Pi will be available. That is the condition for a safe sequence to exist. Right? So if a safe sequence exists, then this can be guaranteed that finally all processes will end by induction. So there is the first process in the safe sequence will end, and it will free up its resources. Using those, the second process in the safe sequence will end. Using the resources freed by these two processes, the third process in the safe sequence will end, and so on. So every process in the safe sequence will end. If this is true, this is what is called a safe sequence, if there exists such a sequence. So essentially, if a system has a safe sequence, then the state is called safe. Okay, if the system has a safe sequence, then the state is called safe. If the system is in an unsafe state, that means a safe sequence does not exist, then the system is said to be in an unsafe state. Then there is a possibility of deadlock. Again, it is not a sufficient condition. See, in this picture, deadlock state is a subset of unsafe states. It's not that all unsafe states has to lead to a deadlock, right? But an unsafe state may lead to a deadlock. So essentially, the OS tries to prevent the system from going into an unsafe state, right? So the operating system ensures that the system is always in the safe state. And for that, it may have to reject resource requests from processes, even though the resource is available. Okay. So let's see an example, which will hopefully make things more clear. So there is one resource type only, and it has 12 instances. There are these three processes. The second column gives the maximum need. As I said, the OS must have some idea of what is the maximum number of resources that each process can need. This the OS needs. And current allocation is shown in the third column. So now the question, does there exist a safe sequence? What do you think? So essentially, is there a process which, with the current allocation and the number of resources that are free, can end? So there are 12 instances of the resource. The current allocation is 9, 5 plus 2 plus 2. So there are 3 instances that are still available. So is there a process which can end? Exactly, P1 can end because it will ask for at most 2 more instances. Maximum need is 4, 2 is already allocated. So P1 will ask for at most 2 more resources. So P1 can end, and then once P1 ends, it releases maybe 4 resources, 4 instances. Using those 4 instances, some other process can end.
4 plus 1, we also had that one extra check.
Exactly.
P1 not can end.
Exactly, P0 can end. Right, so the safe sequence is P1, P0, P2. Right? So again, the online audience also, if you have any questions, ask. But so essentially P1 can end because it will ask for at most 2 more resources types and 3 are available. Once P1 ends, P0 can also end because it will get 5 more instances. And finally P2 can end. Right, so this state is safe. This state is safe. Now, let's say P2 is allocated, P2 asks for a resource. P2 asks for 1 more resource. So it has 2 already allocated. It asks for another resource. Now, suppose that resource is allocated to P2. See, now this state will become unsafe. The explanation is written in the slide. Okay, so if P2 asks for 1 more resource, the resource is free. The resource is available. But if it is allocated immediately, the state will not remain safe anymore. It will become unsafe. So ideally, the OS should not grant this resource right at this point, even though it is free. Okay. So this is how the OS tries to reason whether a particular resource request should be allocated right now or not. So, okay, so how does OS do all these things? How does OS take these decisions? So there are multiple ways again. One is to use the resource allocation graph that we discussed, but we are not going to discuss that. Rather, we are going to discuss another algorithm called the Banker's algorithm. Okay, let's see. So Banker's algorithm makes some assumptions. So it assumes that there are multiple instances of each resource type. And the second point is important. Each process must declare the maximum resource requirements a priori. This is what we saw. Like every resource should declare right at the beginning that what is the maximum number of resources of different types that it needs. And when a process requests for a resource, it may have to wait. As we saw, even if the resource is available, it may not be allocated immediately. Because if the allocation is done, then the system moves to an unsafe state. Okay. And when a process gets all its resources, it must return them to the OS in a finite amount of time. So these are the assumptions. And we are using some data structures. So it's actually simple. Basically, we are looking at matrices. Let n be the number of processes and m be the number of resource types. So we are looking at some n cross m matrices. Let's see. Okay, available is a vector of length m. So the jth element of the available vector says what instances are, how many instances of resource type Rj are there? The jth element of the available vector says how many instances of resource type Rj are there. Max is a 2-dimensional array, n cross m matrix, which gives the maximum number of resources that a process can request. So the ijth element of max array, a matrix, ijth element says what is the maximum number of resources of type j or Rj which process I can request for. There is a corresponding allocation matrix which says currently how many instances of which resource type is allocated to which process. Okay. And there is a need matrix which tells the further need of the processes. Essentially, need the ijth element of need is ijth element of max minus ijth element of allocation. Right? So max says how many maximum number of resource instances a process can ask for. Allocation says how many are already allocated, and need is the difference between these two, max minus allocation. Okay. And there are two notations. Suppose there are two vectors x and y of length n, two vectors. We say x less than equal to y if and only if every element of x is less than the corresponding element of y. Okay, this is one notation we use. So say that one vector is less than the other. And if T denotes an n cross m matrix, we use Ti to denote the ith row of T, which is the vector. So Ti is the ith row of T. So the allocation subscript I vector, that is the resources that are currently allocated to process Pi. This is a particular row in the allocation matrix. And similarly, a particular row in the need matrix, the ith row of the need matrix, that are the additional resources that process Pi can still request. Okay. So now the safety algorithm. So there are two algorithms. So Banker's algorithm is actually a combination of two algorithms. First of all, first algorithm is called the safety algorithm, and the motivation is trying to find a safe sequence. So in the current resource allocation state, is there a safe sequence? That is what we are trying to find. So again, the algorithm is not difficult if you see. So can one of you explain what is going on intuitively? The idea is to find if the current state is safe. That means trying to find a safe sequence. So what is going on?
Find the process such that all its requests are lesser than for each resource, all the requests are lesser than the ones which are available.
So that is step 2, right?
Yes.
So find such a process such that
For every resource, its request is less than the available.
So that process can end. Then what about step 3?
Updating the allocated resources.
Why updating?
It will release those, right? So
essentially, the OS is pretending or simulating as if that process ends. It has not yet ended. But the OS is kind of pretending or simulating the fact that when it ends, when this process, which is identified in step 2, when that process will end later, it will free up its resources. So those get added to allocation. Those get added to work. So allocation I is the current allocation to the process I, Pi. When Pi ends, those resources will be freed and they will be added to work. Wait, and using that, so again we go back to step 2. So see, from step 3 we go back to step 2 again. So again try to find another process. Now is there another process which can end? Yes, essentially you understand we are trying to figure out the safe sequence. Every time in step 2 we are trying to find out a process which will complete using the currently available processes and currently available resources and the resources which will be freed when some other processes will end. So every time if we are able to find this kind of a process in step 2, that means we are enumerating the safe sequence one by one. And if we come to a stage where we cannot find such a process in step 2, that means there is no safe sequence. Okay. So think about it in the example that we studied 5-6 slides back. Mentally, you made the same calculation, like P0, P1, P2. We identified that there is one process which can end with the current allocation and what is free. That was the first process in the sequence. Now we pretended as if that ended. That would end. When that ends, that would release its resources. So is there now another process which can end? This is the same algorithm which we mentally calculated. Okay. So essentially, this algorithm finds out if the current state is safe. Yes, a question.
What if there are more processes which have the need less than the work?
At least one should exist. If there are more, fine.
But it might not lead to a safe sequence in that case. Like we have to backtrack. Let's say there are.
will actually, because if you have two processes, then अगर इसका कम है तो उसमें कुछ ऐड होगा, राइट? तो फिर भी वो जो सेकंड वाला था वो भी कम ही रहेगा. So in the next sequence it can be chosen again.
So you're hypothetically looking at it and checking that even then.
Yeah, even then.
It's a hypothetical case. You are not actually in the resource.
So if there are multiple processes which can, I mean, which say you are saying there are two processes, the P1 and P2, both of which can independently end. That is what you are telling.
Both of them satisfy the second.
Yeah, but at least one should exist. If there are more, fine, one will be chosen. At some, in the next step, P2 can be chosen again. See, there is no hard and fast rule that P2 cannot end unless P1 ends.
It doesn't have to be a unique safe sequence.
It doesn't have to be a
Unique safe sequence.
unique. No, I mean, I have never claimed that safe states has to be unique.
Doesn't have.
No, doesn't have to be. There are multiple safe states possible, and at least one should exist. That's the thing. I mean, okay, multiple safe sequences are possible.
Yeah.
Safe state is whether the state is safe or not, but multiple safe sequences are possible. If there is at least one safe sequence, then the process state is safe. And this algorithm, again, it does not try to enumerate all safe states or all safe sequences. It needs to enumerate only one. Okay, so the safety algorithm basically sees if there is at least one safe sequence. And then there is this next algorithm. Determine whether a resource request can be safely granted. Okay, so how is this? Again, it's pretty obvious algorithm still. So first of all, check if the request is if request is less than need. Okay, if the request I is more than need I, that means this process is doing something illegal. It had initially said that I will request only up to these many resources, but now it is asking for more. So step one says it's an error. Like the process is asking for more resources than it had said earlier that it would need. Next step, suppose the request I is not even available. Then of course it has to wait. If what the process is requesting for is not available now, then of course it has to wait. The OS does not have to take the decision whether to allocate the resource or not, because it's not possible. The resources are not free. The question comes if what the process is requesting for is available currently. So that is step 3. So if the control reaches step 3, that means that the resources that the process is requesting for are available, right? So then what the OS does, pretend that, okay, I suppose I allocate these resources. Now will the state remain safe? So as part of pretending to allocate the resources, these adjustments are needed. The 3 adjustments which are given in state 3. Think about it. These are the exact manipulating the data structures in order to pretend that the OS is allocating the resources. The OS is not actually allocating it. I mean, it is trying to decide whether to allocate in actuality or not. But if it would allocate, then this is how the data structures would change. Okay. So this is again a simulation that suppose the OS thinks, suppose I allocate all these resources. So now this will be the state. Okay. Now check if that state is safe. How to check if the state is safe? The previous algorithm, the safety algorithm. Right? So pretend that the resources are allocated, then check if the state is safe. If yes, fine, go ahead and actually allocate the resources, make adjustment to the data structures. If not, if no safe sequence would exist, if these allocations were made, then don't make the allocations. Because ideally the system should never enter as an unsafe state. Okay. So yeah. So actually the order in which we studied the algorithms, the actual use is in the reverse case. So first the resource request algorithm is run. And as part of it, it is checked whether the next state, if the resource allocations were to be made, would remain safe or not. Okay, so we studied first the safety algorithm and then studied the resource allocation algorithm or the resource request algorithm. Actually, these algorithms are run in the reverse sequence. First this algorithm is run. When process PI makes a request, first this algorithm is run. And as part of this algorithm, in say 3A, the step 3A, the first bullet point under 3, that is where the safety algorithm is run. Okay.
So when we run the safety algorithm, then isn't the allocations already happening?
No, I think pretend to allocate. So the OS just updates the data structures. It makes a copy of the data structures and updates them. That is a pretension that suppose I allocate, then how would the data structures look like? It just makes a copy of the actual data structures and changes them. And then it checks whether the state would be safe. Yes.
So when suppose I first ran the safety algorithm, so I got
Wait, why should you run it first?
So if I get a safe sequence, then isn't it guaranteed that if I keep on allocating in that sequence, then there won't be a deadlock?
Okay, so your proposition is that you would run the
Safety algorithm.
safety algorithm first.
Yes.
I see.
Then I get a safe sequence, and then I keep on executing them in the safe sequence. So isn't it guaranteed to not cause an issue?
Okay. Theoretically, possibly you are correct. But think what might be a practical issue.
Yet here it is that the request is dynamic. So like in that case, this works better, I guess. Because in that, what I'm saying, there we need to know everything a priori. But since here we have the bullet point 1, so like the request is more than the need, right?
Yeah, sure. Okay, 1 and 2 are there, right? Okay. But suppose 1 and 2 checks are passed, and then we are talking about stage 3. So maybe from a theoretical point of view, what you are saying might work. But again, I'm also not completely sure, but from the top of my mind, it seems. Remember, safety algorithm, like actually we discussed this a few minutes back, there can be many safe sequences. The safety algorithm will find one of them. But whether that exactly corresponds to this allocation, if done, I'm not sure, like if it is so straightforward.
Some processes might give more resources on completion, and some processes will give less resources.
Sure, that is there, of course.
That's why we have to do this type of sort of factoring.
Yeah. Besides, see, I mean, is there really a lot of difference? See, steps 1 and 2 are kind of error condition checks. So in step 3, I mean, apart from just updating these 3 vectors, then immediately the safety algorithm is being called. Right.
Here we'll be running the safety algorithm multiple times, right? After each process.
Yeah. Here.
Yeah, here. Only
no,
once.
why? Why? In step 3, you are running safety algorithm once. Why multiple times?
Aren't we doing this for each eye? After each eye?
After, no, wait. A particular process only has meta request, PI. So this algorithm needs to run only once, right? Okay. This algorithm will run once for every request made by every process. But for a particular request, this algorithm runs only once. The thing that you are possibly mixing up is with this. This runs many times. Because see, there is this go to step 2 and so on. Right, so this has to work, this has to run multiple times. Okay. Okay. Okay, see now let's understand. I think there is 10-12 minutes more material left. Should we complete it today? Or do you want to come back tomorrow at 9 a.m.? All of you are early morning risers.
Complete it today.
Complete it today, yeah. I mean, this is a choice which, like, no algorithm is needed to understand. Yeah. Fine. So again, in the online audience, if anyone is awake still, we are continuing the class for some time. If you are awake, you might have been awake for some more time.
Yes,
Okay.
sir.
Okay, great. By the way, any questions about this?
Mark Jindal is requesting control.
Why? You think you are the OS? It's trying to preempt all of us. Anyway. Okay. Okay. So fine. Yes sir बोलने का ही एनर्जी बचा था. Question कौन करेगा? Fine. Now coming back. Okay, just in case there is a detailed example given. I'm not going into this, but if you have understood the algorithm, just go through this. The slides are already uploaded. Just go through this example. These things would become clear. Okay. So yeah, this is quite a detailed algorithm. A detailed example. So actually, a particular state will be explained. This one, and then a request would be. So initially the state is safe. Then you will see a particular request is made. Okay, and then this example will, I mean, explain that it is still safe to allocate those resources. Okay, fine. So just go through this example. I think the algorithm would be clear. It's intuitively simple. I think you have understood the idea. Just go through this example. Okay. So remember, beginning of today's class, we talked about two broad types of approaches. One is deadlock prevention or avoidance. Then the system completely avoids that the OS completely avoids that the system will reach an unsafe state. The other one is, okay, let the system reach an unsafe state or deadlock, but then detect it and then do something about it. Okay, so the next type of method that we will study is deadlock detection and recovery. So again, there are lots of complicated algorithms which assume that there are multiple instances of each resource type. But for this class, we are not going to discuss them. We are going to discuss a simple algorithm, a deadlock detection algorithm, which assumes that there is a single instance of each resource type. Okay. So again, we will consider a graph-based method, which will draw inspiration from what we discussed earlier. If you remember, we discussed a resource allocation graph where we had two types of nodes, resources and processes, and we had edges. So getting a cycle in that graph might indicate a deadlock, right? So we will do something similar. So here we will maintain a graph which is called a wait for graph. Again, pretty simple. Here the nodes are only processes, and there is an edge from Pi to Pj if Pi is waiting for Pj. Yeah. Okay, there is a directed edge from Pi to Pj if Pi is waiting for Pj. I think intuitively you understand that this kind of a wait for graph can be derived from the resource allocation graph. Okay, here is an example. The resource allocation graph has two types of nodes, processes and resources. And just from that, you can derive the wait for graph because you can understand, like say here, P1 is in the left-hand side figure, P1 is waiting for R1 and R1 is allocated to P2. That means P1 is waiting for P2. So you have an edge from P1 to P2 in the wait for graph. Okay. So, I mean, it's simple to understand how this graph can be derived from the resource allocation graph. So once you have done that, it's easy. Just look for a cycle in this wait for graph. Remember that circular wait condition. There has to be a sequence of processes such that in a set of processes, there has to be a sequence that P0 is waiting for P1, P1 is waiting for P2, and P2 is waiting for P0. So essentially in this wait for graph, if you can find a cycle, then there is a deadlock. Okay. Now, again, remember from our graph theory knowledge, detecting a cycle in a large graph is not a very cheap operation. So it's order n square, right? So it's kind of inefficient. Okay. So remember, these graphs are not very small. There can be many processes in a system at some point of time. At a point of time, there can be actually many resources in a system. Many processes in a system. So in this graph, there can be thousands of nodes. And therefore, detecting a cycle in that kind of a large graph requires order n square time, which is not very small. And of course, if you consider multiple instances per resource type, then algorithms are even more complex. We are not discussing them. If you are interested, you can look up the internet to figure out some algorithms. But they might be even more complex than order n square. Okay, now suppose this has been done. So someone has run a cycle detection algorithm and has found a cycle in the wait for graph. Fine, so there exists a deadlock. Now what to do? So the deadlock has to be like destroyed, right? So what to do? Essentially two ways, either terminate some processes or preempt some resources from a process, right? Again, linking back, if you see, these are two ways which will falsify one of the necessary conditions for deadlock. Okay, so once you have discovered a deadlock, how to recover from it? First thing, process termination. But yeah, actually sounds more simpler. It's not so simple, because which process will you terminate? Whichever process you choose to terminate, it might be said to be unfair to that process. Okay, one thing, like about everything, like about all deadlock processes. Do you think that's a good way? Not at all. I mean, who would like our processes to be terminated in that way? Okay, slightly more conservative approach, about one process at a time until the deadlock cycle is eliminated. Or then in which order? Which is the process which will be first terminated? It will be unfair to that process in some way. So okay, people have tried out different methods like priority of the process. Like start with aborting low priority processes in the increasing order of priority. Then maybe how long the process has computed. So if a process has already been running for a long time, should it be terminated? Well, maybe yes, because it has already run for a long time. But again, maybe it has done a lot of computations already. So now if it is terminated, all those computations will be wasted. Right, so like easy to propose things, but actually quite difficult to implement in practice, like which processes to terminate. Okay. The other way, okay, so process, yes.
Can't you just select one process to terminate because anyway it is a cycle? So
Agreed, but which process? Okay, and besides, you never know that just by terminating that one process would be enough to, again, if all the processes are in a cycle, then yes, only one process terminating would be enough. But you never know. Maybe. Right, so, but yeah, say within code's best case, you have to terminate just one process. But still, which process? That's a difficult question. Okay, slightly more conservative approach, don't preempt processes, don't abort processes, but preempt resources. So some of the resources which were given to a process, maybe all of them are waiting, right? They are deadlocked. So take back resources from some process. So again, same question at a slightly lower scale, but same question. Which process should you preempt resources from? Remember, preempting a resource might not be so easy. That process might have been in a state where it has, say a resource is a shared read-write file. Maybe the process has already made some changes to the file. Now, if that is preempted, then other things can go wrong. So the third point becomes important, rollback. If you want to preempt some allocated resource from a process, then the selected process may have to be returned to some previously known safe or consistent state and restarted later from that state. Has this idea have you come across this idea in some other course? Rollback? Exactly. In database also, there is a concept of rollback. Taking the system to a previous known consistent state and again restarting from there. That's a very costly operation. I mean, should not be done every minute or something. Right. So, but yeah, these things can happen. Like because you had allocated a resource, now you are preempting it. So, I mean, this might need to be done, rollback. And then there are starvation and so on, etc., etc. Okay. So again, it's not easy to implement in practice. Okay, fine. So we have 2 slides left, but so here, you see, we have discussed a lot of things: deadlock prevention, deadlock avoidance, deadlock recovery. But then I guess now, I mean, you had asked the question long back. Maybe you are seeing that nothing is so straightforward here. So, okay, we have ways for Banker's algorithm. Fine, the algorithm seems simple. But then it has a very strong assumption that all processes declare a priori what resources it will require. That's not practical, right? Think about it. Like even you cannot dynamically allocate memory. If these conditions are so strict that every process has to declare in advance what is needed, then all these, the programming will become quite difficult. Dynamic allocation of memory, then creating variables just like that, all these things might be problematic at some point. Again, so deadlock avoidance seems, too high requirements. Then we came to deadlock recovery. So there we talked about detecting a cycle in a large graph. That's inefficient, not n square. And even if you are able to detect a cycle, or a deadlock, which process should you abort? Which process should the OS abort? Which process should the OS preempt resources from? So these are easier said than done, right? So these are theoretical ways, but in practice, difficult to implement all of these, right? So what is done in practice? This was the question which I said I would answer later. So in practice, what is done is what is called the ostrich algorithm. So pretend there is no problem. Deadlocks are not very common, right? And the cost of prevention or detection is very high. So understand that, so basically Unix, like very popular operating systems like Unix and Windows, they simply do not do any deadlock detection, recovery, anything. Why? Are these algorithms too difficult to code for OS developers? No, then why not?
Not difficult to code, but like very unfair and like,
Yeah, very unfair.
For the user to.
Yes, agreed. Any other reason?
Not actually needed too much.
Yeah, because deadlocks occur very rarely. Anything else? No, theoretical guarantees are available. As in, another big reason is that if the OS, like every time it runs this kind of a deadlock detection algorithm and all, new processes have to be run because of them, which will require more resources. So essentially, it will end up worsening the situation. Remember something we had discussed in the very first lecture of the course. The OS does not think itself as important. The OS tries to take as less resource as possible. It tries to take as less time as possible on the CPU. The OS understands that the tasks that are done as part of OS or kernel, they are actually overhead in some way. Because the computer system is not to do kernel processes. We pay money to do our work, not the kernel work. So if the OS starts taking too much resources, too much CPU time and so on, that is actually detrimental for the user interests. So that is why people of Unix and Windows designers, they said, just forget it. And besides, they depend on something else. So see, deadlocks are rare, but still can happen. Then what? As I said, as written in this slide, Unix and Windows do nothing about deadlocks. Sometimes deadlocks can happen. Then what?
Kill the process, I guess, when you realize it.
Exactly. So the OS designers rely on our impatience. They know that if many users see that their processes are not progressing, some of them will be impatient and kill their own processes. Okay, so the deadlock will be resolved. Right, so often they rely on our impatience.
It's another way of assigning priority, right?
Yeah, who is more patient that way. Yes. So essentially, choosing which process to abort, that decision no longer needs to be taken by the OS. Let the users to figure out. Then there will be no complaint of unfairness because I have killed my own process. Okay. So essentially, nothing actually is done in deadlock prevention in most of the popular OS. Okay. And I guess, okay, and this slide answers another question which was never asked. But can anyone guess what the question is? You have guessed lots of answers. Now, can anyone guess a question which was never asked, but this slide answers it?
Why are we writing our assignments in? There could have been deadlock detection.
You have not done any assignments on
No, I
deadlock.
mean, like in that case, my assignments wouldn't have taken so much time to detect where the deadlock is occurring.
Huh? But there was no deadlock detection in
I'm
algorithms.
saying like while coding, I need to take care of that. There are no deadlocks, right?
Using logs.
Oh, no. That was synchronization. Wait. What do you mean?
I'm talking off the topic. I know that.
Uh-huh.
No, I mean, he is basically, I think.
No, even if it's a joke, we need to understand that, right?
It's
I mean,
not quite a joke, actually. I think there is
it's
a
a
gap
satire.
in understanding.
Uh,
So correct me if I'm wrong, Ashutosh, but you are saying that in locks, like you need to actually talk about deadlock. So that lock A, like the process holding lock A, does not depend on a process, like someone should not wait for the lock indefinitely.
So
And
if,
he has ways to
so if my
stop
OS
that.
already told me that here is a deadlock, so like I wouldn't have to debug. I wouldn't have to take half an hour to debug it, right?
So he had done some primitive deadlock prevention while holding locks and going into
okay.
critical section.
Okay. Okay, fine. Now at least I understand. Yeah. Okay, now at least I understand what.
This is what I'm saying, right? I mean, there are more elaborative primitives and building blocks that we haven't even covered here. So there's no way that you can use them. Or you can, but not like
Anyway, so the question I was looking for is like the question that was never asked. Why did we keep this chapter for the end? In any book, you will find it earlier, but we kept it for the end because we wanted to discuss the more practical aspects earlier, like memory, file system, and so on. Okay, so officially the last slide. Yeah, a summary. But
The
yes.
simple reason was that we had less time, so we wanted to make sure that
we wanted to practice.
Yeah, of course. Yeah, we wanted to prioritize the practically more important topics. So, by the way, so this is called an ostrich algorithm, this last one, because I don't know the reality of this, but it is said that an ostrich, when it sees a danger, it rather than running away, it buries its head in the sand and pretends that everything will be okay. I really don't know. I have not seen an ostrich doing that. I'm sure if I approach an ostrich, it will not even care. It don't think me dangerous, but yeah. Okay, any questions?
I have one.
Yes, to whom? Okay.
Why do we study deadlock and why is there a chapter on deadlock in all the operating system history? Not used.
So Mainak is asking a question that if this is the case, then why is there at all a chapter on deadlocks in all OS books?
Right, and they don't want to analyze us. Why do we need this knowledge?
now I know those 4 conditions, right? So like I can take care of those while writing my code. That I make sure that they don't happen.
As the OS doesn't have such a algorithm to predict deadlocks, it is his responsibility to write good code to avoid these situations. So, in order to make us aware about these.
So that we do not write the deadlock prevention algorithms while designing.
You may come up with some.
It's ultimately finding cycles and graphs.
So Mainak, maybe you might.
Is there any other?
No, but I mean, you might be a bit louder and tell the answer.
So the question is.
I would
Yeah, go ahead.
I would suspect that some like real-time OSs might have deadlock detection because there you cannot really pretend nothing is happening. If processes get stuck, then the power plant blows up or something like that.
Fantastic answer. Anything else? No, think in that line. Look, the whole point is that you learn this because will be useful to you some way.
To come up with newer versions of OS which can.
In specific cases, yes, there are. I mean, even now, like something called Fuchsia is being developed, which is microkernel, started in 1995. Google just gave its first commercial version in 2018. So yes, new OSs are coming in. The new devices come in, new OSs will also come in. Real-time systems, one. Anything else? So the point is that deadlock happens. Okay. Operating system does not need to. One of the reason is that operating system themselves is handling a lot of resources. When do you think that operating system will give the control of reading and writing disk to a process? Never. You always have to go through system call. Operating system knows everything. Now go to the application layer when you have direct memory access, talking to the peripheral and doing all those fancy stuff that you need to sometimes. And suddenly you will have deadlocks because you ran like three processes. One is getting the stream from your camera, and there is analyzing data. Third one is running a deep learning algorithm. You got deadlock. So in your application layer, you need to do deadlock prevention. OS does not do that simply because OS already have, like, for example, like this bankers algorithm or all of these things, what they actually tell is, and you also have producer consumer, right? All they tell, if you have a priority of having resources and releasing resources, you will not have most of the deadlock. Connect it back to producer consumer, planning philosophers. When you do not have such luxury of having a centralized system of acquiring and releasing resources, you will have deadlock. One key application of deadlock that we use every day in a database. Multiple processes try to actually access database columns and rows. You'll have deadlock if you're running any very if you're running complicated query which depends on multiple resources in the database. I'm not going to details. Many of you have not done database. But that is the reason. And if you have questions regarding in an application scenario, it is acquiring this resource and is there a deadlock, don't be surprised and don't tell that this doesn't happen in real world. This will happen in the application layer, not in the OS perhaps. And the reason is that operating system takes in, it's a centralized system, right? Like almost like kernel thread is like almost always one thread. It knows when it is taking in resources, when it is releasing resources. Do it with priority, you will have not have most of the deadlocks. Does this make sense? So you are imposing a total order on the resources, total on the resources, and taking in that order. That is what is sort of already imbued in your operating system code.
So you're saying that the level at which the problem is solved or needs to be solved is different.
Still, there might be deadlock when the operating system cannot give a total order. There's a partial order, and then you are pretty much messed up. That's where I think Deep was mentioning real-time systems, Rocket, Break. You cannot really afford to have deadlock. In your brand new BMW, if it had deadlock when you're like going on 200, pushing 200 on a highway, it's not gonna be good. So they have something called absolute deadlines. Not a term, but essentially you need to meet deadline for each and every process. Otherwise, you need to kill some processes. Which process to kill? In those cases, they are very well defined. You cannot kill the braking process. You can definitely kill your sound system. Make sense? Okay.
Well, this happened during the first moon landing as well. Basically, while the LEM was approaching the lunar surface, there were too many operations going on. So there was a deadlock, and the computer force restarted itself. So the moon, it almost never landed, but then there was this protection scheme that ensured that the critical systems were actually on.
Any case, so deadlock is important for that reason. If you are given an application scenario, you have to think about deadlocks, especially when you are talking into peripherals and other resources, shared resources. So Ashutosh, your effort is not wasted. You needed to do that because you're working at the application layer. I think that would be.
Yes. Any announcements?
Okay. So a couple of announcements for whoever is going to listen to this recording and whoever are here. One is that we will, like the grade sheet, it still is, I understand it's still probable potential in the works, in the sense that it will be finalized after Sunday. Tell your concerns, discuss, they can update the numbers, but after that, after Sunday, it's frozen. I think that's reasonable, right? Okay. Second, we will have the lab viva. Don't fret, 10 minutes each, but we want to know individually and also bask in the glory that how well you learned after doing this really lengthy labs. So we'll test mostly from the assignments that you worked on. If you have worked on it, there's not much to study. If you have not, well, we'll see.
So for the lab viva, I think the expectation is, or the syllabus, the expected syllabus would be the
assignments and the concepts used in the assignment, concept, function calls,
concept, system calls,
algorithms. Like essentially, what did you use? You already gave the demo, right? So tell us why and so on and so forth. This is just a validation check again, but it will consider a non-negligible marks, say 10 to 15%. Just so that you take it seriously and we can have our final validation and lab test. But nothing to be too heavy. You already have your exam week in front of you. Okay. We will announce the syllabus and the schedule for your lab viva soon by this weekend. But that is sort of the.
And the timing would be the next Tuesday's lab hours.
Yes.
So keep that place free. Do not schedule anything else then.
Yes, please don't. Because if you cannot attend it, we cannot really redo the viva. It will be extremely difficult to reschedule. And it's 10 minutes of your time. I think that will be all mostly.
So any questions from anyone about the logistics?
So we would have more questions. We take more questions about logistics on MS Teams as usual. But if you have any burning questions in your mind, like, I really need to know that as soon as possible, please go ahead. Any questions? Aryan, Deep, Simant, Sant, and whoever is there, Srijan?
No, sir.
Okay.
Fine.
So we are waiting for TA's replies. So yeah, that's okay.
Sure. You have still like 3 more days to actually talk and get back, and you have time.
Yep.
Fine. Okay then. Thanks everyone. Yeah.
Thank you.
So we'll end the meeting.
Yes, and also actually before we end, I think we can stop the recording. Yeah, perfect.